vectors get pretty interesting once we start introducing the dot and cross products. These dot and cross products are really useful in a lot of geometrical applications. When we're first learning about these two products, it can be a bit weird at first. So in this video, we hope to run through some of the key ideas, some of the key uses of these two products. We'll also run through a few exam type examples to see them in action. Let us start with the dot product. We'll use an example to figure out what the definition of the dot product is. So given two vectors, in our example, we'll use the vector 1, minus 2, 3, and another vector, minus 5, 2, 1. So when we do the dot product, we want to find a way to combine these two vectors together. So we will multiply the numbers across component-wise. 1 times minus 5 give us the number minus 5, minus 2 times 2 give us the number minus 4, and 3 times 1 gives us the number 3. Instead of writing them as a vector this way, minus 5, 4, minus 4, 3, we want to add these three numbers up. So the dot product gives us the final answer. We add up minus 5, added to minus 4, added to 3 gives us the final answer of minus 6. So we define the dot product to be this way. We multiply them across component-wise and we add up these three numbers to end off with a number. The dot product is also called a scalar product because the final answer is a number or a scalar. So this was pretty weird to me at first. The natural thing to do will be this thing I've just described. We multiply them component-wise and end up with a vector minus 5, minus 4, 3. So why is the dot product defined this way rather than this way? Why is it defined to be why do we want to add up the three numbers rather than leave the final answer as a vector? So the reason for this is turns out that when we are studying geometry and the applications like angles and distances, turns out this number minus 6 is a lot more useful than this vector minus 5, minus 4, 3. In fact, this vector hardly turns up at all in the study of 3D geometry. However, the number minus 6 will be very useful in certain calculations if you want to find the angle or we want to find certain lengths. To see this in action further, I have written a blog post talking about some of my own difficulties in learning the dot product, as well as a proof of how this definition of the dot product will allow us to go to a very useful formula that we will see later on in this slide. Okay, so this is so a reminder, the definition of the dot product is we multiply them across component-wise and we add up the resulting three numbers. Another remark I want to mention is that the square of a vector, we do not define it. So given the vector 1, minus 2, 3, for example, if you want to square it, it's pretty natural to think of, I want to get the vector 1, 4, 9. Turns out again that is not quite useful in 3D geometry, so we don't define the square of a vector at all. Instead, if another idea of a square is you can take a vector and use the dot product with itself. This is defined based on our rules we have set up above here. So the reason the dot product is defined this way, ending up with a scalar, is because it leads to this formula over here. This formula reads a dot b, the vector a dot vector b, equals to mod a mod b cosine theta, where mod a is the magnitude of a, mod b is the magnitude of b, and theta is the angle between the two vectors. If you're interested in how this formula can be derived from our definition, once again, I have made a link to the blog post I have written about this subject. So when do we use a dot product and when do we use this formula? There are two main applications where we often use this. The first application is to find angle. So we are interested to find the angle between two vectors or two lines. We can make use of the dot product formula. Rearrangement of this formula gives us cos theta equals to a dot b over mod a mod b. This formula is very useful because the dot product is actually pretty simple to compute. A dot b involves multiplying a few numbers and adding them up. Magnitude of a and magnitude of b is also reasonably simple to calculate using a square root and Pythagoras theorem essentially. So because the right hand side is very easy to compute, we can just plug into this formula and use our calculator to arrive at the angle between two vectors. A second application of the dot product is to check whether two things are perpendicular. So when we say something is perpendicular to something, it means the angle between vector a and b is 90 degrees. Cosine 90 degrees is 0. This means that if two vectors are perpendicular to each other, the dot product should give us the answer 0. So to check whether two things are perpendicular to each other, we do the dot product. If the answer is 0, it means that the two of them are perpendicular to each other. If the answer is not 0, it means they are not perpendicular. So very useful. We no longer have to use our old formulas to find out whether things are perpendicular or not. The dot product can take care of it for us. Let us move on to the cross product. So the cross product is quite a bit harder to compute compared to the dot product. So let's use this example to understand how this is done. So we are given two vectors, the vector 1, minus 2, 3, and the vector minus 5, 2, 1. And we want to define this thing called the cross product. To get the first component of the final answer, we cover up the first row and go in the cross motion. Take -2, multiply with 1, go across this way. Then we go the other direction, 2 multiplied by 3 gives us 6. For the first component, we take -2, -6 to get this first component answer as -8. Let us now look at the last component over here. So we cover up the last row, and then we go in the cross motion again. 1 times 2 gives us 2, -5 times -2 gives us 10. So we take 2 minus 10 to gives us -8 as the last component. For the middle component, it will be done similarly, except that on the outside, you have to add an extra negative sign to it. So cover the middle row, go in the cross motion. 1 times 1 gives us 1, -5 times 3 gives us -15. So we take 1 minus -15. So 1 minus -15 is 16. But at the end, for the middle component, remember to add the minus sign in front of it. So our final answer is -16 for the middle guy. So the cross product of these two vectors gives us the answer -8, -16, -8. The answer is a vector, so the cross product is also sometimes referred to as the vector product, compared to the scalar product, in which we have a final answer as a scalar. So the definition, why we define the cross product this way, the reason is it gives us something very special. So if, let's say, consider this vector as the vector d1 and this other vector as the vector d2, the cross product gives us a very special vector, the vector n, that is perpendicular to both the original vectors as shown in this picture. So this is a very special concept unique to 3 dimensionals. So in 3 dimension, the vector d1 and d2 gives us, crossing them gives us this vector n. So this vector n is also sometimes called the normal vector. So similar to the dot product, we also have a geometrical formula for our cross product. So the formula goes this way. When we take vector A, cross with vector B and take the magnitude, it's equals to the magnitude of A, magnitude of B, sine theta, where theta is the angle between the two vectors. So the dot product gives us a cosine and the sine cross product gives us a sine. So when do we use the cross product? There are two situations where this cross product is really useful. In the first situation, as we have discussed before, the cross product gives us a normal vector, a third vector that is perpendicular to the original two vectors we used. So if we have two vectors A and B and we want to find a third vector that is perpendicular to both of them, we use the cross product to obtain it. The second use is related to this geometrical formula, mod A mod B sine theta. Hopefully this formula should look pretty familiar to us. If we recall from geometry, we may have encountered the formula half AB sine C as the area of the triangle. So to obtain the area of a triangle, we can use vectors and the cross product. So if we have a triangle over here, ABC, we take two sides of the triangle and express them as vectors. So in this example, it's a vector AB and vector AC. We take the cross product of them, take the magnitude, and multiply by half, and that it will give us the area of the triangle. Two triangles give us a parallelogram, so magnitude of A cross B will give us the area of the parallelogram formed by vector A as well as vector B. These are the main concepts related to the dot and cross product. So let's look at the example question to see how we can use these in the context of a geometrical application and in a similar vein to an exam question. The question goes this way. Referred to the origin O, the points A and B have coordinates 1, -2, 0 and 1, ½ 5 respectively. The point M lies on the line segment AB such that AM is to MB equals 2 is to 3. Show that OA and OB are perpendicular. For part 2, we need to find the angle AMO, and for part 3, we will find the area OMB of the triangle OMB. So let's think about what some of the concepts we can use for this question. So for the first part, we have the point M lies on the line segment AB such that AM is to MB is 2 is to 3. Hopefully this reminds us of ratio theorem, which we have covered in the previous video. For part 1 of the question, we need to show that these two lines are perpendicular and we can use the dot product to achieve that. Part 2, we need to find the angle. That's another use of the dot product, so we'll use the dot product again. For part 3, we are interested in the area of a triangle. This is where we will use the cross product formula. So for part 1 of the question, we need to show that OA and OB are perpendicular. To do that, we can use the dot product. So let's try OA dot OB. So OA is given by 1, -2, 0, dot OB is given by 1, ½ and 5. So let's carry out the dot product. Remember, we multiply them across, but our final answer is not a vector. Our final answer, we add up the three numbers. 1 times 1 gives us 1, -2 times ½ gives us -1, 0 times 5 gives us 0. So we add up these three numbers and end up with 0. So since our dot product is 0, since OA dot OB is 0, OA is perpendicular to OB, and that answers our question. For part 2 of the question, we are interested in the angle AMO. So we use the dot product formula to arrive at the angle. However, before that, we need the position vector of M. How to get that? We have the ratio. Given the ratio AM is to MB is 2:3, sorry. So we will use ratio theorem over here. Okay, so using ratio theorem, we have OM is equals to, we cross multiply, 2 times OB gives it plus 3 times OA over 2 plus 3, which is 5. So let's simplify it. We get 2, 110 plus 3 minus 6, 0 over 5. Adding the vectors up gives us 5 minus 5 and 10 over 5, which simplifies to 1 minus 1 and 2. Okay, so before we apply the dot product formula, which vectors do we need? We need the vector MA as well as the vector MO. So MA is given by our position vector formula, OA minus OM. OA is 1 minus 2 is 0. And OM, we have just found 1 minus 1, 2. So simplifying it gives us 1 minus 1 gives us 0. Minus 2 minus minus 1 gives us minus 1. And 0 minus 2 gives us minus 2. Okay, next we need MO, which is negative of OM, which is minus 1, 1, and minus 2. So let's use our dot product formula. So plugging in MA and MO, we have 0, minus 1, minus 2, dot, minus 1, 1, and minus 2 equals to the magnitude of it. And cosine theta, where theta is the angle we are trying to find, the angle AMO. So let's carry out the dot product. 0 times minus 1 is the number 0. Minus 1 times 1 is minus 1. And minus 2 times minus 2 is the number 4. So 0 minus 1 plus 4 equals to, magnitude of this guy is square root of 1 square plus 2 square. And the other guy, square root of 1 square plus 1 square plus 2 square. Cosine theta. Rearrangement gives us, cosine theta is, this side gives us 3. And we divide it across square root 5 and square root 6. Okay, so theta is given by cos inverse 3 over square root 5 and square root 6. So let us get a calculator to compute the value. And we have the answer of 56.8 degrees, correct to 1 decimal place. For part 3 of the question, we are interested in the area of the triangle OMB. So we can use our cross product formula over here. So taking A and B as the sides of the triangle. So for this particular question, we will have the vector OM and OB, which we found earlier on. So the area of triangle will be, OMB will be given by half magnitude of OM cross OB. Okay, so let's plug in what we have for M and B. So OM is given by 1 minus 1, 2. And OB is given by 1 half and 5. Okay, so let's compute the cross product. For the first component, we cover the first row, minus 1 times 5, getting minus 5. 2 times half gives us 1, so minus 5 minus 1. For the second row, we remember the extra negative sign outside, and cover the middle row, go 1 times 5, minus 1 times 2. Finally, cover the last row, go 1 times half, minus 1 times minus 1, so minus of minus 1. Okay. So minus 1, 5 minus 1 gives us minus 6. 5 minus 2 is 3. And half plus 1 gives us 3 over 2. Okay, so computing the magnitude gives us 36 plus 9 over 4. Okay, let's go to our calculator to get the answer. So plugging in our calculator gives us an answer of 3.44 units square for the area of the triangle. The dot and cross products are also pretty useful in calculations of certain distances and lengths. So let's take a look at that. Let's understand the idea of vector projection using this example. So in this example, we have a vector A over here and vector B. Let's imagine B to be the floor and A to be some kind of a ladder, and there's a sun shining above. So what shadow does the ladder cast on the floor? So it will be of the length OF. So we call OF the projection of vector A onto vector B. So to obtain the length of it, we can use some trigonometry to derive it. So the length OF is the adjacent side in this right angle triangle. Adjacent sides are related to cosines, which are related to the dot product. So we have a formula that the length of projection of vector A onto vector B, which is this length OF over here, can be given by A dot B hat, where B hat is the unit vector of B. So if you're interested in the derivation of this formula, feel free to post a comment below and discuss some ideas you may have, or I may chime in to show you the solution as well. So next, we may be also interested in the vector OF itself. Instead of just how long it is, we are also interested in what the vector OF is. If you recall from the previous video of the use of unit vectors, so here we have OF. OF is parallel to B, and we know the length of OF is given by A dot B hat. So we can obtain the vector OF by A dot B hat multiplied by B hat, the unit vector. Finally, sometimes we also be interested in the perpendicular distance from the point A over here to the line OB. So to get to that we want the distance AF. AF is the opposite side in this right angle triangle, so it's related to the cross product. So we have a formula. Magnitude of A cross B hat will give us the perpendicular distance. Sometimes we will have to work with vectors abstractly. If we look back at example 1, we are given the coordinates of points A and points B. So these numbers will allow us to perform our calculations of the dot and cross product. However, sometimes, like in example 2 we're going to try later, we are only given the vectors A and B and not told what they actually are. And all answers are to be given in terms of A and B. In that case, we probably have to use some algebraic manipulations to arrive at the final answer. So this page summarizes some of the rules and algebraic manipulations that we may want to carry out. This will probably be a bit dry. Hopefully we can work through it, and we will see them in action in the next example to come very shortly. So the first rule says that anytime you encounter a constant, you can drag it out of a dot or cross product. So in this case, the number k can be dragged all the way out, similar to for the cross product. This should be pretty familiar, as it is pretty similar to some of the usual algebraic rules we have. The next rule says that the order is not important for the dot product. So if you take A dot B, it's the same as B dot A. So hopefully this is pretty intuitive and clear from the definition of the dot product. However, do be careful with the cross product. The order is important for the cross product because of how it's set up. So if you want to switch the order around, we have to add a negative sign to it. This rule, we have to be pretty careful about it. Next rule, very similar to usual algebra, tells us that we can expand vectors. So A dot B plus C will be, if after expansion, A dot B plus A dot C. The similar rule applies for the cross product. For cross product, just be a bit careful because the order is important. For this expansion, we have to be careful that A is on the left and B and C are on the right. If we switch the order, we will have made a mistake. If we really want to switch the order, we have to use a negative sign to compensate for that. The last rule tells us what to do when we dot a vector by itself as well as cross a vector by itself. The way I remember the last two formulas are using the geometrical formulas. So A dot B is given by mod A mod B cosine theta. The angle between A and itself is 0 and cos 0 is 1. So application of this formula gives us A dot A is mod A squared. Sine 0 will be 0, so A cross A will be the 0 vector. So now let's take a look at how some of these formulas can be used in the example. So we look at the example over here. So the question goes, refer to the origin O, the points A and B have position vectors A and B respectively, where A and B are non-parallel. The point M lies on AB produced such that AB is to AM is 3 is to 7. Find, in terms of A and B, the position vector of M. For part 2, we have find the area of the triangle OMB in terms of vectors A and B. For part 3, given that magnitude of A is 3, B is a unit vector, and that angle AOB equals to pi over 3, we will have to find the length of projection of OM on OA. So what are the key ideas we'll use for this question? First, we have ratio theorem, because we have a ratio over here. However, this is a tricky application of ratio theorem because we are given that AB is produced. That means we extend AB and M lies outside of it. We'll see it in action later. Then to find the area of the triangle, we'll use our cross product and our abstract algebra like shown in this slide. Finally, we also need the length of projection of OM on OA. That is our dot product formula. Magnitude of A is 3. B is a unit vector, meaning the magnitude of B is 1. So we use all of these in action as we work out the solution. So we are given that M is on AB produced, meaning AB is made longer. So M lies outside of it. The ratio of AB is to AM is 3:7. So AB is 3 units long, AM is 7 units long. So BM is actually 4 as a ratio. Okay, so connect it to the origin to use ratio theorem. So how does ratio theorem work in this case? Ratio theorem gives us the guy in the middle. So if we start off with question 1, ratio theorem gives us OB is equals to, cross multiply, 3OM plus 4OA over 3 plus 4, which is 7. So we are given that OA is vector A and OB is vector B. We will plug that in and rearrange our equation, multiplying the 7 across. 7B equals to 3OM plus 4A. We make OM the subject, which gives us 7B minus 4A over 3. And that's our answer for part 1 for OM. For part 2, we are interested in the area of the triangle OMB. So we apply our formula. OM and B, the sides of the triangle are given by OM and OB. So applying our cross product formula, we have area of triangle OMB is given by half magnitude of OM cross with OB. So written abstractly, we have OM is 7B minus 4A over 3 cross with the vector B. So here is where we will use some of our abstract rules. First, the 1/3 is a constant, so we can bring it out of the cross products. So we have half magnitude of 1/3, 7B minus 4A cross with B. Okay, next we will do expansion. So we have half. The 1/3 can be dragged out as well, so we have 1/6 magnitude of 7B cross B. We're expanding, and minus 4A cross B. Okay, if we refer to the previous notes we have, A cross A will be 0. So similarly, B cross B will be 0. So we have 1/6. This is 0, so it cancels out. Minus 4, A cross B. Okay, minus 4, when we drag out of the modulus, we get 4/6, which is 2/3. Mod of A cross B. And this is as simplified as we can go, and the answer asks us to express our answer in terms of A and B. So this is actually the answer already. So for part 3 of the question mentions the length of projection. So if you recall our earlier formulas, so now I change the letters around so to avoid confusion. The length of projection of P onto Q is given by the formula P dot Q hat, where Q hat is the unit vector for Q. So for this particular question, we find the length of projection of OM onto OA. Okay, so let's apply our formula. Our length of projection of OM onto OA is given by magnitude of OM dot OA hat. OA hat is given by OA divided by its magnitude. Okay, then we plug in what OM is. OM, we found it to be 7B minus 4A over 3. Okay, dot A over magnitude of A. Okay, so how do we proceed with this complicated algebra? First, the constant can be dragged out, so we have 1/3. We can expand 7B dot A minus 4A dot A. Okay, and everything is over mod A. Okay, and this is where we proceed with further formulas. 7, B dot A is given by mod B, mod A, cos theta. A dot A is given by mod A squared over mod A. We're given all these quantities in the question. We're given that magnitude of A is 3, B is a unit vector, so mod B is 1. And finally, we are given that the angle is pi over 3, so cos theta is pi over 3. So plugging it in, we have 7, mod B is 1, mod A is 3, cosine of pi over 3 minus 4, 3 square over mod A is 3. So let's simplify. 1/3, 21. So cosine pi over 3 is given by half minus 9 times 4 is 36. Over 3. Okay, so if we calculate it out, 21 times half is 10.5. 10.5 minus 36 is negative 25.5. This simplifies to 17/6, which is our length of projection.